Hello, everybody. Today, I can identify rigid motions by checking for orientation. Very, 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 very important. And separately, or related to that, also I can explain why triangles are congruent using a rigid motion preserve size and angle measure, producing a congruent figure. So, I'm going to teach you about orientation and then we're going to get to it. So you can actually see me. Woo! Here I am. That looks so good today. That's okay. So here's how orientation works. I've got a button side. I've got a back side. We'll call this the front. We'll call this the back. If I perform a transformation and I see the same face, then the orientation is the same. If I see the opposite face, the orientation is different. So if I perform a translation, do I still see the same face? Yes, I still see the front. Therefore, a translation preserves orientation. If I rotate it, do I still see the same face? Yes, I still see the button side. Therefore, a rotation is a preserves orientation. If I do a reflection, if I flip this, do I see the same face? No. So a line reflection changes the orientation. However, what if I do a second reflection? Now it's back to where I started. So I'm going to do that again. A single reflection changes the orientation. A double reflection brings it back to where it is and preserves it. So only a single line reflection changes the orientation. And finally, if I take this calculator and I make it into a giant calculator, if I dilate it, or a tiny calculator, do I still see the same face? Yes, a dilation preserves orientation. So what you need to know is that they all preserve, let me write it down here, they all preserve orientation except for a single line reflection. Now remember, a point reflection is technically a rotation. A point reflection does preserve orientation. Only a single line reflection does not. So how do I check for orientation on a graph? Well, we're checking the order of the letters. So it's telling us the order of the letters here. Q, R, S, T, U, V, W, X. Q, R, S, T. I'm going to draw arrows going from Q to R to S to T. This direction is going clockwise. If I follow these around, it's going clockwise. U, V, W, X. U to V to W to X is going clockwise. They're both going in the same direction. If they're going in the same direction, it means that it has the same orientation. If it has the same orientation, I know that it can't be a single line reflection. So what can it be? Well, point reflections, we're not going to, since a point reflection is a rotation, we're not going to really talk about point rotations unless it tells us to do a point reflection. So let's just look at it as a translation and a rotation. You got to use a little bit of geometric common sense here. What's happening here? Is it a rotation or a translation? It's a translation. It was slid. So we need to be a little bit more specific. It's a translation. How much? So let's count. Let's pick any point and its image. Let's go R to V. How do I get from R to V? Well, it's 1, 2, 3, 4, 5, 6 to the right, and 1, 2, 3 down. So it's a translation, 6 right, and 3 down. Now, make sure you pay attention to which one you're starting with. It says maps QRST onto UVWX. That's why I started here and I went there. Are they congruent? Use the properties of rigid motions to explain your answer. Any rigid motion, any translation, reflection, or rotation is a rigid motion. It always preserves a congruent figure. So, is it congruent? Yes. A translation is a rigid motion. So I'm stating that what I did is a rigid motion, and then I state the definition of a rigid motion, which you'll hear in your song, in your class, and that is a rigid motion preserves size and angle measure, producing a congruent figure. A rigid motion preserves size and angle measure, producing a congruent figure. It's always the same definition. So whenever you do a translation, a rotation, or a reflection, and it says, are they congruent? The answer is always yes. A, whatever I did is a rigid motion. A rigid motion preserves size and angle measure, producing a congruent figure. Let's take a look at number 2. I want to identify the transformation. I start by checking for orientation. A, B, C, D, E. A, B, C, D, E. J, M, W, Y, H. Is the orientation the same or different? Well, this one here is going clockwise. This one here is going counterclockwise. It has opposite orientation. Which is the only one that has opposite orientation? A single line reflection. It must be a reflection. A line reflection. So now you have to look for the reflection. If you can't see it, you could always count between it. But in this case, that's your line of reflection right there, the y-axis. So it's a reflection over the y-axis. Let me start typing. I don't know why I'm writing when I could be typing. Is ABCDE congruent to JMWIH? Yes. A reflection is a rigid motion. A rigid motion preserves size and angle measure, producing a congruent figure. Key is to check for orientation. If it's the same, it can't be a single line reflection. If it's different, it must be a single line reflection. Once you find that it's a reflection, you gotta use a little bit of geometric common sense to see what it is. We could also count from any point to its image. So like B to M is 1, 2. It's going to be halfway, so we cut that in half and we find the line there. But that's not going to be a big thing for where we're going with this. Number 3. Check for orientation. So I got BAM, B to A to M. This is going counterclockwise. I've got H to U to M. This is going counterclockwise. They're both going counterclockwise. Orientation is the same. So it can't be a line reflection. So we're left with translation or rotation. It's pretty clear that that's a rotation. So what are we doing? Rotation has to be very specific. It's a rotation of how many degrees? Well, since it's turning completely upside down, it's 180 degrees. You have to state a direction For 180, it doesn't matter if I go clockwise or counterclockwise because it's the same. So I'm just going to say clockwise, centered at. Now we need to state the center of rotation. Whatever the shapes are touching, that's going to be the center of rotation. So in this case, the center of rotation is going to be at M, centered at M. So again, you need to be very specific for rotations. You have to tell me how many degrees, which direction, and what the center of dilation is. Are the triangles congruent? Yes. A rotation is a rigid motion. A rigid motion preserves size and angle measure, producing a congruent figure. And that's it. Let's take a look at a couple more, and then I'm going to move on. Identify the rigid motion that maps ABC onto AFD. Well, ABC, A to B to C, that is going clockwise. AFD, A to F to D, that is going clockwise. They're both going clockwise. Therefore, the orientation is the same. Which means there can't be a single line reflection. So then what is it? It's not a translation. It's not just a slide. It's a rotation. So you have to use a little bit of geometric common sense as far as how many degrees and which direction. I see it. I'm starting with this one, the green one. It's going this way. So it's going counterclockwise. And that's a 90-degree turn. We also said that every 90 degrees, it moves one quadrant. That's a 90-degree turn. So it's a rotation of 90 degrees counterclockwise, centered at. Now again, the center of rotation, if there's a point that didn't move, that will be the center of rotation, in this case A. Are the triangles congruent? Yes. A rotation is a rigid motion. A rigid motion preserves size and angle measure, producing a congruent figure. And that's it. Now number 5 looks kind of similar. Let's take a look at 5. And this will be the last one I go over now. Check for orientation. It's very similar to the last one. A, B, C. A to B to C. That is going clockwise. A to F to D. And again, you're looking at the letters that are here. A to F to D is going counterclockwise. The orientation is different. Orientation, therefore, there must be a reflection. The reflection is the only one that changes it. So, what am I reflecting over? If there's a point that's touching, that point's invariant, that point's got to be on the line of reflection. So if you use a little bit of geometric common sense there, that is going to be my line of reflection. It's a horizontal line, so it's y equals, from Yancey has X-ray vision, and that's y equals positive 1. So it's a reflection over the line y equals 1. Are the triangles congruent? Yes. A reflection is a rigid motion. A rigid motion preserves size and angle measure, producing a congruent figure. And that's it. Check for orientation. If the orientation is different, it must be a reflection. If the orientation is the same, it's not going to be a reflection. It could be a rotation or it could be a translation. For rotation, use a little bit of geometric common sense as far as how many degrees, and the point that's touching is the center. Make sure you state the direction as well. For reflection, again, use a little bit of geometric common sense, and if there's a point that's touching, the line's got to go through that point. For a translation, you're just telling me the direction, how much it's going. All right, if it's going 6 right and 3 down because you counted that it went 6 right and 3 down, then that's all you're telling me. Practice this. We're going to build on this lesson. And that's it.